The universal conditional statement combines the idea of an existential statement, this for all plus a predicate, with a conditional statement. Specifically, the predicate is a conditional statement with variables. Right? This is one of the most common constructions that you're going to see in mathematical theorems and proofs. And like the existential and conditional statements, there are multiple English variations that we can use. So these three examples here all follow the standard format that you see in the definition. Each one starts with a domain, right? Real numbers here, real valued functions here, and rectangles here, right? Followed by a conditional statement. Now, every universal conditional statement can also be written in a purely conditional format by taking the domain and moving it into the antecedent of the conditional statement. For example, the first statement here could be written if x is a real number greater than or equal to 1, then x squared is greater than or equal to 1. The second statement here, if you think about it for a second, right? Maybe see if you can figure it out yourself real quick before I talk about it. The second statement could be written if a real valued function is differentiable, then it's continuous. And finally, the third statement would be if a shape is a rectangle and all four sides are congruent, then it's a square. Now, you could reasonably ask, right, why we need this new universal conditional statement if it could just be rewritten as something we already have, right? And I think this last statement really kind of illustrates that. The language of the conditional version is a little strained, right? Sometimes it's clearer if you split the domain out and then use the predicate part just to talk about the specific properties that you want to focus on. In this case, the behavior of the sides and what type of quadrilateral it is. Now, we can also go the other way around and rewrite a universal conditional statement as a pure universal statement, right? For example, the first statement here could be rewritten for every real number x with x greater than or equal to 1, we have x squared greater than or equal to 1. We could write the second statement as all real valued differentiable functions are continuous. And finally, for the third one, for every rectangle with 4 congruent sides, the rectangle is a square. Or the rectangle, let's say, is also a square. Now, I want you to kind of notice what I did in each of these. Right? If the original statement was for every x in D, if P of x, then Q of x, what I did was I rewrote this as for every x in S, Q of x, where this S here, right, where this S is an appropriately chosen subset of the original domain D. All right, so S will be a subset of D. For example, looking at the second example here, the original domain D was real valued functions, but in my conditional, in my universal version, the new domain S was real valued differentiable functions, right? A subset of the original domain. And you see this again, we can see this in the third one here. The original domain was rectangles. My revised domain in my purely universal version is rectangles with 4 congruent sides. It's a subset of the original domain. Now, hopefully at this point, right, you're starting to see the utility of our symbolic language, right? While the English versions may be nominally easier to understand, the variety of options can sometimes make it challenging to tell exactly what's being said, right? The symbolic versions avoid that issue by having a single consistent format for each type of statement. Right, so looking ahead to the next lecture, we're going to continue our discussion of existential and universal statements, right, by thinking about what their negations are going to be.